Hi everyone. So I'm really glad to be here, being invited as speaker. And today's my session will be around exploratory data analysis, which in short is called as EDA. A little about me. So I think most of the introduction it was already being given. So I'm currently working as a data scientist at Srijan Technologies, and my experience mainly lies across building ML and deep learning based applications, then deploying them over the cloud infrastructure, and then managing the scalability part, which is ML ops basically. And also, I have been extensively working on the optimization part as well for the algorithms. So let's look at the things that we are going to cover in this session. So first, I will be giving you a walkthrough about what an EDA is. Then we will be looking at some of the important terminologies like that we will mostly come through. We will like if you will start exploring the data, then you will come across these topics and you may be confused. Like you will be confusing in most of the things because they are quite new. So yeah, we will have to look at those things as well. Then after that, we will be looking at like what a descriptive statistics is all about. So we will be just looking at some simple terms, I think, which most of you are already familiar with. And after that, we will have some introduction about like what is a univariate analysis, then bivariate analysis, and some dimensionality reduction techniques, most of which are already discussed in the previous section. So I will not be going into that much detail. We will just be touching upon those things. And then I have some a slide where I will be discussing about like what is the process of whenever we are bootstrapping an ML project, and like what are the process behind those things. And then that will like conclude our session. So let's get started. So what is an EDA? So before like we will get to the definition, what actually an EDA is, there are a few questions that I would like to emphasize on. So let's say like we got some data and we will be like we are yet to start with the EDA part. Then there's an always a thought that should we start using machine learning on top of that data. So the actual thing is like I see in the industry most of the times, most of the problems, we are not using machine learning at all. Like most of the problems are basically you can just solve it using some simple image processing technique or maybe some rule-based techniques. So like most of the time you will not be using machine learning. That depends on the requirements, like what kind of problem you are solving. And then definitely like whether you will have the data or not. So how can we like get to know about like these things? Is this a right time to pick up ML model and get started with it, or like should we are just fine with any sort of rule-based algorithms? So there comes the EDA part. Like through EDA we can conclude these facts. We can have some solid points that yeah, this is the right time to use machine learning algorithms because we have these characteristic in our data set, and yeah, we are good to go with this data. Then there can be another problem. Like there are very like various diverse range of algorithms out there, right? There are a lot of linear models, there are a lot of non-linear models, and there are deep learning techniques and lots of things out there. So how are we going to pick a particular algorithm? Like there should be some selection criteria, right? So how can we jump upon those things? So that should be also like that will be clear once we will have a proper EDA of our data set. And another important thing that if you will like be working as a data scientist, then most of the time you will be like you will be facing these challenges. Like you will be asked with your by your manager, like what are the sort of features that has a great impact on the business. So let's say you will be you are working as a data scientist in a credit card company, and your manager has asked that, tell me what sort of features are converting more fraud detection things. Then you will have to jump upon some sort of characteristic in your features, and with the use of that you can just get back to your manager, and you can say that, yeah, these are the things that heavily impact our decision making, and through these things we can say that, yeah, these things are the important indicator that, yeah, uh, uh, through these things we can just caught the fraud detection thing. So there are a lot of nitty gritties that we will have to kind of look into our data, that we will have to be aware about before starting with the modeling phase. So that's where EDA comes in. So EDA, if I will basically like introduce you to the definition, I think now's the right time, because we have some knowledge about like what sort of question that we can expect. Why is there is a need of an EDA? Then I would say that EDA is basically a kind of an art. So it's a kind of way to visualize your data, to understand your data, get familiar with it, like what sort of characteristic are inside your data. Is this like, is your data really ready to kind of process through some mathematical models, or do you need some other sort of data, or those kind of things. So EDA is kind of, we can say it's a kind of big detour, right? Because there are no hard or soft steps that you can follow. And through that, you can say that, yeah, this is a proper step. And we can say that, yeah, we have our, we followed these steps, and we have some information about our data. So you will have to learn through practice, after trying several plots, after trying several things, you will have to learn those things. So that's what an EDA is basically. So if I will if I will show you like in a real data science world where exploratory data analysis fits in, then let's say we have like you are working for an e-commerce company, which is what here I'm showing as a reality. Then you might be collecting lots of data, right? You might be collecting user activity data, like let's say if you are a user, you are visiting an Amazon site, right? Then there are lots of data being generated out there, right? Because whenever you are clicking some item, whenever you are making some transactions, whenever you are just browsing, there are lots of data generated with those activities. And those things are captured by the companies, right? And on top of that, where the analysis part comes in, on top of those data, you can build your models, you can make the business decisions. So there those things comes in. So the first part is like collecting those raw data. Then once we will process those raw data, and we will have a clean data set, then we can do the exploratory data analysis on top of our clean data set. Now, if you will see this flow chart, so like once we will have the exploratory data analysis, once we will have the result and I would say insights from the exploratory data analysis, then only we can go to this step, like models and algorithms part, then building let's say a product out of our data, or maybe communicating or visualizing report or dashboards, and making decisions with those dashboards. Then only we can proceed with proceed to that part. So, so I would say EDA is the first step if you have your clean data set. And in every data science problem, it is, I would say, not the first step in a data science problem, because obviously you will have to collect the data and then process it, then clean it and those kind of things. But yeah, one of the initial process from where your data science problem starts. So I think, yeah, like we have some good intuition about what an EDA is. Now let's look at like how EDA is majorly performed. So these are the key points that I want to elaborate on. So like there are descriptive statistics that we can use. Then there are univariate and bivariate analysis, and multivariate analysis. as well. So we will look at these points. And then dimensionality reduction technique, I think, which was discussed in the previous session as well. So these are the things like that are majorly performed as a part of EDA. So some of the important terminologies that I want to discuss, because whenever you will be like being exposed to some data, then you will see that, yeah, these are the terms that you will come across, and it would be very much helpful for you to kind of have some previous good introduction about these things. So let's talk about features. So if you, let's say you have a CSV data set, then there can be different columns, right? And those columns are basically features. So if I would say to like what kind of characteristic those variables have. So basically we classify them into two different parts, and one of which is called as a categorical variable, and the next one is called as numerical variable. Now, of course, these are very simple terms, but my main motive is to kind of just to organize these things so that you can have a kind of good mind map, and you can relate these things whenever you will be sitting with some data and doing some work or some analysis on it. So if I will talk about like what is a categorical variable. So categorical variable are basically, it tells us about the quality of our recorded observation, right? So like we can have categories like eye color, or maybe say, let's say we have some polling data, then we can have maybe some political parties where we can just say that, yeah, political party is basically what, just a category. So that was like the categorical characteristic of a variable. And then there comes another characteristic on the basis of what we can say that, yeah, it's a numerical variable. Now, what is a numerical variable? So it basically tells us about the quantities, right? So now, of course, if we will talk about quantities, then there can be two scenarios. One where you will find that in most of the cases it will be a discrete kind of quantity, and in some cases it will be a continuous kind of quantity. So discrete is basically like a countable things, uh, something which we can count, like number of children, then defects per hour, and those kind of things. And continuous is basically like weights and voltages. We can explain these terms in a continuous terms. So just a basic simple terms. Then there's another terminology that I want to discuss. It's called missing values. So in statistics, missing values basically when we have no record for any observation. So let's say we have a CSV data set of age, weight of a person. And let's say in some row, we found out that one of the value is not there. It's just an empty. Then we describe this situation as a missing value situation. And there are in some of the data set, maybe you can have some flags as well. Like you can have some -1 or maybe NaN as a flag through which you can identify that, yeah, this is a missing value and you need to treat them. So there can be multiple things which you will have to kind of find out yourself by exploring your data, like by visualizing certain columns, by visualizing certain descriptive stats and those kind of things. So another thing is the problem comes in like how to handle this missing values. So let's say we have some certain missing values. Now the problem is like how we are going to treat it, right? So the first thing is like understand the region, like what could be the reason that your values are missing. And another thing could be the main thing would be to like get a better understanding of your data. Like you once you will have some good domain knowledge what a data is all about, then you can think in some wider terms, like what could be the reason that this particular value is missing. So the another like mathematical technique, if I would to discuss, then it would be called maybe an interpolation. You can use like using some related values to interpolate it to the missing values things and those things. Then there can be some ML models that you can build spatially for imputing these values. There can be some descriptive statistics that you can use to impute these values. So that depends, and you will have to try out with all these things, and you will have to see that what is working best for you, because there are no rules for this. So one of the example I would like to discuss would be, let's say we have a gender column in our CSV data set. Let's say we have a CSV data frame, and there's a gender column. And let's say we have a name column as well. So name along with the titles. Now, what if there is one column, there is one record we found out in a gender section and it's missing. So if we will be looking at, like, if we will look at the name, then I think with the use of that, we can easily impute those things, right? Like if there is a Mr., if there is some name starting with Mr., then we can easily say that, yeah, then we can just impute, we should impute that value with the male category. So these are some of the things like you may found out while you will be working with some data. And this can be very helpful. So this is basically what a domain is all about. Understand your data better, and then make the imputations and necessary steps on the basis of your understanding. Then other thing is outlier that I want to discuss. So outlier is basically something which is very different from your normal observations that you have recorded. So in, like, whenever you will be building your model, there are some of the categories of models which are very kind of prone to failure relating to the outlier thing. Because if you are, let's say, using, if you will be building a linear model or some non-linear model, then those things are kind of heavily impacted by the outlier. So if you will not treat the outlier properly, then you will just mess up with your result. So that's why an outlier can cause a very serious problem, and it's really critical to kind of treat it properly and handle it properly. So now the question comes in, like, how can we treat outliers? So should we drop them or should we replace them? So again, like, domain plays a very important role here, because let's say we have a age category in our data set, and there's an age which having a value of let's say 330. And then we can obviously like we can have as we have a good understanding what an age of a person can be, then obviously 330 will not make any sense, right? So like, that's how you can use the domain part again here. uh, like, if you will understand your data, then you can have some of the information like, yeah, this part is not making any sense, and you can just then replace it with maybe some maximum age that a person can have, let's say 110 or 100, whatever you think, and just try out with those things and see like what is working good for you. Then another thing you can use is maybe not the maximum age of a person, maybe some mean, median age of your data. You can impute the outliers with those things. So another thing you can use can be a clipping method, which is basically substituting the 99th percentile value for your outliers. So we will be looking at, like, what is this percentile and those things in the upcoming slides. So the main idea here is to treat the outliers properly, because it can seriously mess up your result. And some models are really heavily dependent on these things. Then another thing is the normal distribution. I think most of you are already familiar with these concepts already, but I just wanted to kind of reiterate on that. So a normal distribution is basically a distribution where you have mean, median, and mode. All these three quantities are kind of overlapping with each other. So here in the figure, as we are seeing, we have like mean, median, and mode. All of these three things are kind of overlapped with each other. And we have a kind of symmetrical feature here. If we will look at the midline, so let me just use a pointer here. So if we will look at the midline here, then we have a proper symmetry here. if you will look at this half part and this particular half part, then we have a proper symmetry here. So that is also one of the characteristic of a normal distribution. And if you are seeing these characteristics somewhere, then you can easily conclude that, yeah, this is a normal distribution. Another beautiful characteristic of a normal distribution is like it satisfies this particular rule. So the number you are seeing here, now where does that came from? So if you will look here, so this is basically the standard deviation. This is one standard deviation, two standard deviation from the mean, and three standard deviation from the mean. So the rule says that in the first standard deviation, like when we will go left or right from the mean in a normal distribution, one standard deviation left or right from the mean, then we will have 68.3% of our data set lying here. So that's what this rule says. Similarly, like if we will go two standard deviation left or two standard deviation right from our mean, then if our distribution will be normal, then we will have 95% of our entire population living here in this range. And similarly for this 99.97, which is three standard deviation away. So these are some of the characteristics which normal distribution has. And if you will have, if you find these things inside your data set, inside your data set distribution, then you can say that, yeah, this is a normal distribution. Now, you might have heard that like a lot of time, there are a lot of focus on normal distribution, like why it's needed, why do we need to convert our distribution to normal distribution. So the thing is, like most of the ML algorithms, they are dependent upon these things. Like if the things will be normally distributed, then once you will do the mathematical modeling through that data set, then you can have some smooth curves, smooth gradient descent, smooth learning with that distribution. That's why we always like, we always tend to kind of convert our data into a normal distribution. Then there's a term which is called as normalization. So normalization is basically nothing. In a layman terms, I can say that normalization is just converting your distribution to a normal distribution. So there are some of the methods that you can use. So I'm not going into the details of these methods, which is G-score, power transform, log transform, and min-max scaling. You can explore these things later on. You can easily find these things on the web. There are lots of articles there. But the main motive here is to kind of convert your distribution into a distribution that will be normal, so that you can have some good mathematical model with that data. So here, one of the kind of figure that I found over the internet just to make things simpler. So let's say we have this distribution. We had this distribution earlier. So if we will normalize it, then let's say we will use some G-score normalization. Yeah, I think they have used G-score normalization here. So let's say we are using G-score transformation for this distribution, then our distribution will convert into this kind of distribution. And now if you will see here, we have some proper spread in our data, because earlier it was just a jumbled one. We had our data set all collected in just a kind of jumbled form. Now we have some spread, and we can our model can now smoothly do the gradient descent. Our learning curve will be kind of smooth, we can say that. And that's why like the normalization is very important thing that you will have, that you need to do for your data set. Especially if you are using deep learning or neural nets, then there's a batch normalization layer that you will have to, that always will benefit you. So that was for the normalization. Now we will look at the descriptive statistics. So in the descriptive statistics, basically it is just to describe your data set. So with the use of descriptive statistics, you can just have a kind of quick summary of your data set. So most of the terms we are already, I think most of you are already aware about: mean, mode, median, then standard deviation and variance, then some of the terms like skewness and kurtosis. But don't worry, we will have a quick look at these things as well. So let's look at mean, median, and mode. So we can, like mean is simply the sum of all those things divided by number of observation. Then median is just the like sorting your data into an ascending order, then selecting the whatever the value comes in the middle. And mode is basically just based on a frequency. So that was mean, median, and modes. and let's look at some of the real life examples. So all of us are using Play Store, right? Google Play Store. So if you will, whenever we are downloading some games or some apps, we look at the ratings. Now, like, have you ever been you have like, did you ever think of like how those ratings were converted? So basically, mean is behind the scene. Like, let's say we have 5-star rating, 4-star rating, and these kind of ratings, and these were the users that gave those ratings. So, and we generally see that it's showing, Play Store is showing us 3.5 or let's say 4. So these ratings are being calculated through the mean. So you can just look at this mathematical calculation that I have mentioned here, and we are getting around 3.42, which is basically, if we will round off this value, then we will get around 3.5. Then another example for the median will be like, if I would ask you, like, calculate the average income for our country, then in this case you will not be using mean, because mean will be pretty much kind of a spurious measure. Because if you will talk about income, then it's highly imbalanced. There are highly rich persons out there, there are highly poor persons out there. So mean will be kind of very much spurious. So in that case, you can use median. You can just sort out those incomes, and you can just select the middle one, which is a median. So just a simple term. And then for the mode, the best example could be like, all of us are using YouTube. When we see like the most viewed videos on YouTube, then that is an example of mode. And let's say if I'm looking for some hotels at a particular site, and if I'm searching for some popular hotels, then that will be the example of a mode. So that was something about mean, median, and mode. Then there are variance and standard deviation, which you can use for the descriptive statistics. So variance is just simply like subtracting mean from your observation and then dividing it by the, and then doing the square and then dividing it by the number of observation you have. So standard deviation is basically just the square root of variance. And like I have mentioned the formulas here, and I think we have these kind of intuition from the earlier, right? But these things are used at, like, these things are widely used for the descriptive statistic thing. So it's better to kind of have a kind of quick mind map of these things, so that we can think in terms of these mathematical equations. So there are some real life examples of a variance and standard deviation could be, let's say, if you are doing some customer survey. Let's say you are a market researcher and you are doing some customer survey. So like you all know that customer survey are done on generally some sample of a population, right? So how can you be sure that those results that you are getting from the survey results, those are enough reliable? So in these kind of scenarios, what you can do is you can just use this variance and standard deviation. So let's say if you have a very little standard deviation, then that is a very good indicator that you can rely on your results, because there are very less noise in the decision making. Like each customer, whatever the population you selected for the customer survey, then you can easily say that, yeah, there is a very less standard deviation, and we can easily conclude that, yeah, it's highly reliable, and we can use it for the larger population. And the another example would be kind of you can use it for the outlier detection and removal purpose as well. And similarly, as like we discussed before, there was a G-score term. So in the G-score term, we also use kind of a standard deviation as a denominator. So that was some example of the standard deviation and variance. And let's talk about skewness. So skewness is basically just a measure of symmetricity of your distribution. So you can see that this distribution is kind of has a tail around right side, and this has a tail around left side. So we quantify these things as a positive skewness for this particular case, negative skewness for this particular case. So we can have skewness as a positive, zero, negative, or maybe undefined in some cases as well. And we generally use skewness and one other term that we will be looking, which is called as kurtosis, to kind of get an intuition about what kind of distribution we are having with our data set. So this will give you basically just a single number, and with that single number, you can just, without plotting, you can have an idea like what kind of distribution, what shape of distribution you are having, and what should be the next step that you should be taking. And this is one of the example. Like here we are having a negative skewness, and skewness value of -1.60. And if you will look at the distribution, then we have a tail towards left, right? So it's kind of there are just less number of observations that we are having in the left side, and most of our observations are kind of on the right side. So if this will be the situation, then we will be having a negative skewness. Similarly, if there will be an opposite situation, then we will have a positive skewness. So these are just of the illustrations that I've just wanted to show, just to kind of visualize, making things simple, like how it looks like when we have a positive as well as negative skewness. So now if you will do some analysis for some data set and you will get some skewness value, then you can easily say that, yeah, I am getting this much positive value, and it means that this should be the distribution that my data set is something like. Some real life examples of skewness could be like people's income, and let's say number of children in a family, and maybe a number of accident claims by an insurance customer, and these kind of things. Now let's talk about people's income. So people's income, why I'm saying it has a positive skewness, because there are like how positive skewness looks like. So this is how positive skewness looks like, right? So if you will talk about people's income, then there can be a lot of population that will lie around some low to medium salary range, right? And there can be very few number of people that will be lying around a very high salary range. That's why if we are going to plot that distribution, then it will look like something look like this shape. And that's why we are saying that it has a positive skewness. Similarly, for all other cases. Then we have another term, which is kurtosis. And kurtosis basically tells us about like the height and sharpness of the distribution. So we always like calculate kurtosis and relative to the normal distribution. So we generally compares it with like if it would have been a normal distribution, then what it would have been. So like there are three different types of kurtosis, which is mesokurtic, leptokurtic, and platykurtic. So these three terms, you don't need to remember these terms. So don't put kind of that one's stress, like we will have to remember it anyway. But yeah, it's good to know these terms so that it will not confuse you whenever you will come across these terms. So in statistical terms, like when we will have a mesokurtic distribution, then it will look like this one. Now, if you will just recall what a normal distribution was looking like, so it's most similar to that distribution, right? So whenever we will have that, yeah, this is a leptokurtic case, or this is a platykurtic curve. And some illustrations, some figures that I have, in the case where we will be having a kind of positive kurtosis. So it will look like this one. So we will have our most of the population lying around the center of our distribution. And in that case, we will be having a positive kurtosis. And if it will be flatter, like in this case, then we will have a negative kurtosis. Some examples will be like we can use kurtosis for the outlier detection, or maybe if you are planning to kind of invest something in a stocks, then to get the reliable kind of value of a sample size, you can use Kurtosis for that as well. So that was all about the descriptive statistics. And let's look at the univariate analysis. So univariate analysis is basically analyzing single variable. So it is a very simple analysis from where you will generally start your analysis with. And of course, your variable could be a categorical or continuous variable. And there are some of the methods that you can use for the categorical variables and for the continuous variable. So there are lots of plots out there with the for the categorical variables and for the continuous variables. So of course that will be a kind of huge session if I'm going to cover all those things. So we will be quickly looking at like count plot, which is a very simple plot, and then just a simple histogram plot and little about a box plot. So box plot, I will be explaining that in detail little bit. And the count plot and histogram plot, that is very easier. So let's look at that. So count plot is basically, as the name suggests, it is basically a counting of how many observations we are having. Let's say we have a data set, we have a column of a gender, then this basically shows that how many number of males and females we have in our data set. Very simple. Then next one is a histogram plot. So this is we generally use for the continuous variables. And for this, you will have to decide on like what bin size you want, because first you will have to do this binning. And once you will have this bins, then you can just plot your continuous variable, and then you can have some intuition about like what your continuous variable, how the distribution looks like, and those things. Then the next one, which is very informative, I would say, is called as box plot. So box plot, it looks something like this one. So we will be having a rectangular kind of box, and there will be two tails. So one will be from the at the top, and then another will be at the bottom. Now this simple plot has a lot of information alone. So if you will look at, so let's start with the percentile thing. So this is basically the 20, this is basically called the Q1 range. So Q1 range is basically some just a simple range where you have 25% of distribution lying over here. Now, similarly, if we will talk about this particular line, then this basically says that if we will measure it from here, then it basically says that we have our 50% of data lying between this particular range. Similarly, for this particular line, we have 75% of our data lying between this particular range. And range here is basically nothing. It is just a simple numerical quantity. Like if we, let's say we have a data of age, then we can have a range of age maybe from 1 to 83 or maybe 100. So that's what a range is. So minimum in that case will be 1, and maybe maximum could be, let's say if we will have an outlier, then let's say it will be 330. So, and this line is basically called as Q3. So like the percentile, as I have already explained, it is basically nothing but like how many percentage of distributions we are having between this range. And this little box, what you are seeing here, it's called as mean. So if you will have a normal distribution, then of course this mean will be overlapping with this line, right? Because what we have learned earlier, it was that in case of normal distribution, mean, median, and mode, all three of them overlaps, right? And now like we can use this box plot even for the outlier detection. Now, how are we going to use for that purpose? So if you will see here, we have something called as IQR, right? So IQR is basically interquartile range. So interquartile range is basically Q3 minus Q1. Q3 is basically this point, and this point, sorry. And Q1 is basically this point. So it is basically just the difference between the 75th value, whatever the value lying at your 75th percentile distribution, minus the value lying at 25% distribution. So if we are going to say that like something which lies beyond the 99th percentile, or maybe uh, at the bottom of, let's say, first percentile, then we can say that we can like point it out that, okay, let's treat them as an outlier. And what you can do is you can just simply replace those values maybe with this maximum value, which is this 99th percentile. So, and let's say if it would be an age, let's say we are talking about age column, then our outlier, let's say there was an outlier and we were having an age measurement of 330, but we know that our 99th percentile of value lies maybe around 93 age. Then we can say that, okay, something which is lying beyond 93, let's treat them as an outlier. And we will say that just replace all the values beyond 93 as just 93. And that's why I was saying that replacing it with the 99th percentile value. And let's say in our case, 99th percentile value is 93. So that was little info about box plot. You can read more about this plot. There are lots and lots of articles out there. And this is, I would say, a very important plot that you should be aware of and that you should use to kind of explain your data. Now, let's compare our box plot with normal distribution. So if we will have normal distribution, then this is what our box plot will look like. So here we are not seeing mean. Well, mean will here overlapping with median. And this is like the tail will look like. Like we have a proper symmetry here. Like if you will measure this particular length and this particular length, then it will be obviously same. So that this is what it will look like in case of normal distribution. Now let's look at the bivariate analysis. So bivariate is basically nothing but analyzing two variables at same time. So basically where here we are doing just a kind of, we are determining the relationship, like how change in one variable will impact another variable. Now there are some of the techniques that we can use for the bivariate analysis. And one of them is stack plot. So let's talk it in terms of categorical and continuous variables. For categorical variables, we have a stacked plot. So stacked plot is basically you will have these bar plots. And so this is basically stacked bar plot. There are another versions for the stack plot as well. You will find it over the internet. But this is basically the kind of bar plot version for the stack plot. So here we have bars, and we have three different categories here: measles, mumps, and chickenpox, three different diseases. And this what basically shows us that for, let's say, uh, so just a second. Yeah. So let's say for first month, for the first month, let's say we have this much number of cases, then we can say that, okay, in first month, within these number of cases, we have this particular distribution for chickenpox, this particular distribution for mumps, and this for measles. And similarly, this for the another next several months. So this basically in a single plot, you can visualize these categories, like for each of the month, what are the distribution for each of these categories in terms of number of cases. Similarly, we have a cross tables we can use for the bivariate analysis as well. So let's say we have a car data set. We have brands like BMWs, Ford, and we have colors. And if we want to visualize like how many number of particular brand in black we have. So you can just use cross tables for those kind of visualization, and it will look like something like this one. Similarly, for the continuous variable, we have a pair plots where you can just plot the pairs of scattered plots between each of the variables. So if I will say this is a petal width and the upper one is a petal length, then what we are seeing here is like this is the scatter plot between sepal length and petal width. Similarly, it will be like there will be plot between each of these variables, like one at a time. So now this is basically suitable for the situation when you have just several variables, because if you will have, let's say, 100 or more than 100 variables, then that will not be feasible. So after that, I will like talk little bit about dimensionality reduction, because pretty much has been covered earlier. So dimensionality reduction is basically used most of the time for visualization purpose, and sometimes even for the mathematical modeling purpose as well. So whenever we have like we want to visualize our data set, so of course the only possible way is to have just a 2D or maybe 3D plots, right? But what if we have, let's say, more than 3-dimensional data set? Then in that case, we can use dimensionality reduction. So there are some techniques that we can use for the dimensionality reduction. So two of the techniques that I will be discussing here. There are other techniques like PCA, TSNE, and some other techniques that you may look at. And these are some of the commonly used techniques that I wanted to discuss. So low variance filter is basically just kind of calculating variance for each of the variables that you are having, and then filter it on the basis of the variance. So just you can just sort your data set based on your variance, and then you can just filter them out. Like whatever will be having a little bit of kind of variance, then you can just filter them out. Then similarly, we have backward feature elimination, where you can just eliminate features using the backward selection mechanism, and where you can just select initially all the variables, and then you can just drop one by one one of them easily, and then you can just see that if there is some change in performance, then you can just either keep it, or you can just throw them out. Like if it is not impacting your performance, then it means that it's not usable. Now, this is the last thing that I wanted to talk about, which is about the process of bootstrapping an ML project. So there are several parts of it, which I would like to talk about. So first part, whenever you will start with a data science problem, is ideation phase. So ideation is basically like to kind of initially start with some data science problem, like to listen to your managers, to listen to your stakeholders, like what are the problems they are facing, and then collect the ideas, research about those things. So this is what an ideation phase is. So there are a lot of process involved there. I'm not going into that much detail because we are running out of time. So the next part that is the part of the bootstrapping is the data acquisition part, where we generally collect data and we do the exploratory data analysis. And once we will have some insights about that, then we can use like research. We can research over some facts that whether it's feasible to develop a particular solution or not. And let's say we have developed some modules, then the next part is kind of validate our modules, like are we getting the performance whatever required for the business case or not. And let's say we are just kind of satisfied with our validation score, then we can just pass it to the delivery team to just kind of launch our project. And the last thing is kind of a monitoring part, where you just monitor your model, like is it performing what it was being expected of, and is it performing well or bad or not, and do we need to kind of reiterate or not. So that's how kind of ML project in a data science world works in. So that was all about, I think, and that concludes